with some standard, you'd aspirate your standard, you look at the counts per second that you get in your standard at known concentration, and you'd get something like, you get, 20,000 counts per second for 1 microgram per mil, let's say. So you could get, for your standard, is 1 microgram per mil, 1 ppm, you might get 20,000 counts per second. Right, for example. And so you get this relationship between concentration and counts per second, just like you do for everything else you've done, and you generate that relationship for your standards, and then you would measure your unknown sample, and you'd get some counts per second, and then you'd interpolate and get the concentration of your sample, just like you've done for everything else. Now the challenge with mass spectrometry, and the reason it's important to have a stable magnetic and electric field, is because it's that field, that mass analyzing field, that's separating your isotopes, and it's allowing you to steer the one you want into the detector. It's the stability of that field that determines how many of those ions hit the detector, right? And so, since you are measuring, typically in 99% of the cases, measuring the standard first and then separately measuring your sample, if there's fluctuation in that magnetic field of the magnet between when you measure a standard and when you measure a sample, you're going to get a different efficiency of ions hitting the detector here versus here. Does that make sense? And what would that produce?
Incorrect results.
Wrong answer. Incorrect results. Right. And so you get incorrect results, and depending on how variable the magnetic field and electrostatic analyzer field was, you get a lot more noise or variability in your counts, rather than have, when you're aspirating your sample, having a counts per second signal that was linear and invariant over the measure of time. You get something that might vary depending on how variable the magnet was. All right, so that makes a big difference, and we'll talk a little bit more about how that manifests in real life. We'll go for maybe just a few more minutes. So the two kinds of detectors that mass spectrometers are fitted with, one is, and the simplest, probably the most robust, is termed a Faraday cup. And it literally is a tiny little cup that looks like a thimble, if you're doing these sewing. It's about as big as the end of my thumb. And it's configured so that it has essentially not a photoactive, but an electron-releasing coating surface on the inside of the detector, so that when you have an ion that comes in here traveling very, very fast, and it strikes this surface, that surface, from that energy that's striking, releases electrons. And those electrons that get released then cascade and generate electrical potential, and that potential manifests as a current that is measured. So there's a direct relationship between the number of ions that strike here per unit time and the number of electrons that are released, and then the current that's generated. And so it converts counts in number of events of an ion hitting per second into an actual current that is measured. And these are relatively robust, not that sensitive, but they work pretty well. On the more sensitive kinds of detectors, and oftentimes mass spectrometers will have both on there, and depending on what you're measuring, you would switch from one to the other. The more sensitive kinds are electron multipliers, and they work just like this, except that they have these surfaces, these diode surfaces, that are actually able to multiply that release of electrons. So, as an example, if you have a detector configuration like this, for example, your ion would fly in, hit the surface here, facilitate the release of electrons. Those would be accelerated to another diode surface where they would impact it and facilitate the release of more electrons. And those would be accelerated here, so you have these not alternating, but increasing potentials to these diodes. And the electrons are accelerating and causing the release of a greater number of electrons, and you magnify or multiply the signal. So that one ion striking here would generate, maybe 1 million electrons, so it multiplies that signal by 1 million-fold, compared to the Faraday, where you get maybe, in this example, a 2-fold, right, increase. And so the advantage is you get a much more sensitive detector. And you can measure here, and we've done this on some instruments here, you can measure an individual event. One ion hitting that detector, you measure that, it's one count. And there's some times that we've measured samples that are so low in some analyte that maybe we get 5 counts per second, or extremely small number of ions hitting the detector per unit time. When more commonly, it's in the hundreds of thousands to billions of counts per second. So in those cases where the abundance is really low, and this was the case that was necessary when they did a lot of the original geochemistry of meteors, and Earth, and all that to figure stuff out, where they would take, there's people in Earth sciences, they would take these crystals of these, there were crystals in some rock formations they would find, they were hundreds of millions of years old, and they would, my recollection is they call these zircon crystals. And these are crystals of minerals that formed when the Earth first, the molten Earth, solidified into a solid 4.5 billion years ago. And they would collect these zircons that are about as big as a fly speck. And they would find these zircons, these rock deposits, knowing that the minerals and the isotopes that are in here were ones that were incorporated into this mineral at the time the Earth solidified. And they could dig these out of the rocks, dissect them in the lab, which they do, and then digest these and analyze the isotopes in these little zircon crystals, and they would be able to glimpse back in time and look at those isotope relationships to when the Earth was first solidified 4.5 billion years ago. And as you might expect, something as big as a fly speck doesn't have a lot of stuff in it, doesn't have a lot of analyte in it. And so they need very, very sensitive mass spectrometers to measure the individual isotopes of the different atoms they're looking at here, so they can understand the relationships between them. And that's one thing they did in how they actually figured out the age of the Earth, is they could go back and understand when the Earth first solidified. And to do that, they had to have technologies like this that allow them to magnify the signals so they could actually measure those counts. Okay, so I'm going to stop here, and we're going to go on this on Wednesday, next Wednesday. Right? We got a class on Wednesday. Now let's take, somebody else. That'll take a few minutes to do this quiz.